And over to Wim.
Yeah, so thanks, Justin, for your introduction. All welcome having you in our today's webinar with BD, TotalCAE, and HPE. And this webinar is actually part of our IT Solutions webcast series. And for those who are not fully aware of this series, I'd like to say a few words about this initiative at ANSYS and our goals also in promoting it to you. So, basically, this webcast series is the place where ANSYS and our HPC and cloud partners are pooling together recommendations and information that we hope can help guide your IT decision making, and whether that is on specifying the new hardware, the new systems in-house you're planning to buy right now, or developing maybe ideas for running ANSYS somewhere else. And on this slide, you can see some of the topics we've already been addressing: security, pay-per-use licensing, Intel technologies, extreme scaling for CFD. So please consider this as an invitation to regularly visit our IT and cloud webcast series pages on ansys.com and make sure that also your IT colleagues are aware of it too. And similar to previous webcasts, we also be recording, as Justin already mentioned, so you and your colleagues can return also to it at some later stage and more convenient to you. So this slide is really meant to show you that our IT webcast series is part of a larger focus at ANSYS on IT solutions. We believe that to be able to productively deploy simulation, the right IT infrastructure is key, and that we need to engage with you on best practices and on how our software fits into your IT environment, because IT really is an enabler for more effective use of engineering simulation. IT matters are clearly driving our product strategy and our engagement also with IT industry partners, including TotalCAE and HPE. And as you can also notice on this slide, we clearly observe three major simulation trends impacting IT. The first one is directly related to today's webinar. It's the ability to do bigger, more challenging simulations and to get also a higher fidelity insight into how your product or process, as you will, is going to work in the real world. And the second major trend is the ability to do more simulations in less time. And as a matter of fact, to run more automated simulation, to evaluate multiple design ideas and reach at a best design that works across a range of operating conditions. So, and a third one I can mention is a trend to provide simulation tools to more practitioners and also engineers who are working in geographically distributed teams who need to collaborate also on common projects. And all of these, as you can imagine, put demands on IT to support engineering at as you will, a new level, a new scale. Let me then quickly come back on the trend of doing more simulations in less time. When we ask our customers in a very large online survey how often they are constrained by turnaround time limitations, it was rather striking that 40% of the respondents limits the size or amount of detail for nearly every model, and 35% limits it for more than half of the time. And then when we ask the respondents, and again I'm talking about thousands of respondents, what they perceive as the solution that could best reduce turnaround time limitations, apart from the majority stating adding more HPC licenses as the solution, 39% responded with replacing hardware by new, better performing, and 27% responded with upgrading existing existing hardware. So in the same survey, by the way, we also asked what they perceive as the barriers to migrate from workstations to HPC. And I can say that the top barriers are the lack of expertise and IT resources to effectively size, configure, and deploy and operate HPC clusters. And that's the reason why we are having today's webinar. We would like to show you why and how to migrate from workstations, from workstation-based computing to an HPC workflow environment. And that brings me actually to today's agenda and speakers. First of all, it's a real great pleasure to introduce our guest speaker, Dr. Chris Bassiano. Mr. Bassiano is a staff engineer and a technical lead for CFD analysis in the corporate computer-aided engineering group at BD, a global medical technology company. And I'm particularly excited to have Mr. Bassiano in our webinar because he will share his insights and experience regarding moving from workstations to an HPC workflow environment with the help of our partners, TotalCAE and HPE. By the way, Mr. Bassiano has 15 years of experience using CFD to investigate non-Newtonian, multi-phase, and porous media flows in biomedical applications. His academic background includes a Bachelor of Science in Biomedical Engineering from the Mercer University and a Master of Science and PhD in Mechanical Engineering from the North Carolina State University. So very pleased to have Mr. Bassiano in our call, in our webinar. And I'm also very pleased actually to have Rod Mack in our webinar. Rod Mack is president of TotalCAE, a managed finite element analysis and CFD private and public cloud service provider. And as a 20-year veteran in utilizing HPC for CAE, Rod Mack will present how they enable ANSYS customers to adopt HPC and cloud by providing a turnkey HPC simulation platform. So Mr. Mack has a Bachelor of Science in Electrical Engineering from the University of Michigan. As the third speaker, I'm very pleased to have Spencer Swift in our call, who will present ANSYS 19.0 benchmark results and some configurations of reference architectures. And quickly looking at his bio, Spencer Swift is aerospace engineer with a background in aerodynamics, CFD, and parallel numerical methods. He has 20 years of experience in HPC applications with SGI and now HPE. And last but not least, we will have a Q&A session at the end of the webinar. And in this session, I'm also very pleased to have Tony DeVarco from HPE in our panel. So let me now hand it over to our next speaker, Mr. Bassiano. Please go ahead.
Thank you very much, Wim. I appreciate the opportunity to talk today. So with that, I'd like to advance the slides to our current next slide here. There we go. All right, so as Wim, thank you very much for that introduction. My name is Chris Bassiano. I'm also joined by colleague Shiva Balasubramanian and Patrick Downey as well, who are also colleagues and managers in our computer-aided engineering group. So we're going to talk about how we've moved from individual workstations to a local high-performance computing cloud, or cluster rather, and then in addition to that, provide some stories along the way of what TotalCAE has helped us achieve. So with that, a little bit of background about BD. We're a global medical technology company with a very broad product portfolio, and our group services is a shared resource that helps bring products to market and analyze products at all the different stages of the company. So you see we have diagnostic instruments, disposable devices, infusion pumps, and even embedded or implantable devices as well. So there's a rather very interesting set of engineering situations that we have to analyze on a day-to-day basis. So our group is called a corporate resource, and we leverage different forms of computer-aided engineering and different technologies to help analyze and solve engineering problems. And one of those areas is through physics-based modeling and simulation, and is integrated with other venues along the way. And we also interact with different stages of the company. It might be manufacturing, it might be quality, it might be R&D, and even gets now into the regulatory department that interacts with bodies across the world even. So a little bit of history, right? So our group has actually existed within BD for a very long time, and BD has had a continued interest and commitment to computer-aided engineering. And we really started with individual desktop machines, where different people would have like kind of a cubicle that had quite a few or extended amount of hardware there, and we would just, you know, run simulations on that hardware. And that worked for a while, and we're able to achieve success and make positive impacts throughout the company. And then we got to a point where, you know, we were space limited. We could not keep adding workstations, so we had to go to remote individual servers that weren't in the cube next to us. They were in another room, like downstairs in a hallway, and they would work for a while, and we would have to share them, though, where each individual did not have a server. So that forced communication to occur, right, that we had to make sure we were sharing the resources well. In addition to that, we would have the 3-year lifespan of the server, where once it would diminish, we'd have to replace it with a new one. And again, we were starting to run out of space on a rack, where it was just, we couldn't keep adding situations. And so one of the things we then looked at was, okay, so what's our next step? Where can we go from here when we had been going from these desktop machines that were Windows-based, servers that were Windows-based, and now we had to look at, oh, what's next? And back in our academic training, both Shiva and myself, we had experience with high-performance computing and clusters, but they were all Linux-based as well. And there were other people in our group that were really hesitant to, like, bring Linux into the equation of how do we do work? Is it really going to be something that we can actually handle? And much less on top of that, Shiva and I also had experiences where we had dealt with high-performance computers, and the maintenance of the high-performance computing center or the cluster is almost just as much as running simulations. And we were talking with Patrick and said, you know, we really don't want to manage the hardware of our cluster. We want to just use the cluster to solve challenging engineering problems, which we have no shortage of. And that's what we want to focus on. And we both had experiences where the cluster, some group gets one, it's a little baby one that's supposed to be awesome, and then all of a sudden one node breaks and another node breaks, and then it just collects dust in the room. And that was not something we wanted to happen to us. And then so we started to talk about with our IT department, and it was like, do you guys have experience with this? And they're like, no, and we really don't want to gain experience with this because we're already backlogged and have too much to do. So this then prompted us to look for partners that would help us make this transition, and TotalCAE helped us provide a high-performance computing cluster on-site locally that they support, they manage, and we are able to leverage the computing resources and not really have to worry about any of the hardware complications associated with that. Now, it's not just hardware, though, that we ended up dealing with. It's also with, now, how do we share resources? How do we work on scheduling? How do we work on submitting jobs? Because when you're in the Windows environment, I click the run button, right? Well, if you have any sort of experience with traditional Linux-based compute clusters, that run button doesn't exist. You have a batch file or a script that's written in some sort of thing called bash RH or something like that, right? So what you end up having to do then is use these odd text editors that you might have any experience with to modify that and submit jobs. Well, TotalCAE has come up with solutions for that as well to help make that possible. But in addition to that, they include a scheduler that was really, really great, because in the past, what we really had to do was we would write sticky notes on machines that were running and say, hey, simulation running, don't restart, don't touch, I have something going on here. Or we even have stories of someone saying, trying to talk to the cleaning personnel of the building and say, hey, let's not clean, don't unplug this computer. I understand you might want to clean the floor, but please don't unplug this, right? And that was when we had workstations. Then we moved to servers, and the servers were remote, so we couldn't just stick a sticky note on it. We would have to use the Windows Task Manager and see if what's our RAM load, what's our CPU load, what individual core is doing. This also got a little bit tricky when, say, we submitted a CFD job or a Fluent job, and all of a sudden the automatic time stepper just started going haywire, and just all sorts of complications started to occur. Well, how do we manage that? How do we know what job is running or what job is doing the problem for that? So that all went away, though, when we used a TotalCAE solution called the portal, where you can use and submit your input files, you can submit your journal files, you can submit the actual Fluent case file even if you want to just submit that. Now, that also, some people love that functionality and that ease of use. We have a blend of expertise in our group, but we have advanced power users that are able to go into the scripts and modify them, and then we also have medium-grade users that if they have specific solver settings that they want, you can add those in as well. So there's really great flexibility there. Now with this, we're able to see and monitor what are the jobs that are running, what are our licenses, who's running what, when do we expect our job to run, and it has provided great capabilities for us to move. Remember the progression I said, sticky notes to Windows Task Manager to now really a web-based application that we're able to just launch very easily, very quickly to gain immediate feedback from. So how have we, we'll use these new tools along the way to accomplish more engineering analyses, right? So one area where we've done this a lot is with high-performance computing and specifically a cluster-oriented distributed computing is with optimization studies, where each of these individual dots represents an individual CFD analysis that we ran, whether it's different flow conditions or different geometries, as you see here with this T-junction. We leveraged our compute cluster to run all this in record time, and we would never have been able to accomplish this many simulations using our remote server, much less our individual workstation capability in a tractable amount of time. So this allowed us to really, really leverage and crank up the type of analyses we could do from an optimization and sensitivity standpoint, where our R&D efforts are able to use these for screening, for down selection, for improvements. It's been very excellent to be able to leverage that. And we're not just running one simulation anymore. There are hundreds of simulations that can get run in similar time frames. So in addition to that, we have alternative types of work that can get done where, so before you saw like an increase in the number of simulations. This is an increase in the technical rigor of a simulation, where we looked at a transient multi-phase flow with a volume of fluid approach, and we added concentration tracking in there as well. And what you see here is that we are also looking at an animation of this. So this also included some post-processing, and this is actually one of our next revolutions, if you would say that, or iterations that we looked at. Our first move to HPC and a cluster did not include a visualization package or a visualization capability. Now, what we recently did is we purchased a remote visualization capability that enables this type of post-processing to be done via a web app, so that you don't need to move the result files off of your cluster to your local machine or to some sort of other machine. While it sits on your cluster, you are able to do the post-processing, you're able to make these animations, you're able to run scripts, and you're even able to now leverage the high-performance computing power for post-processing, which has really helped not have to spend time transferring files, but just digging into the technical results, making technical recommendations, and gaining that understanding from the individual simulations or collection of simulations. So I would say with that, I'd like to thank you for your time, and I'll hand it over to Rod, who will talk more about TotalCAE.
Hey, thanks, Chris. I appreciate it. That was a great presentation, and we always enjoy seeing the journey that people take along the way from Workstations to HPC. So we can just forward the slide here. Let's just take a moment. So when we were talking about, BD definitely saw that they needed to move from, Workstation to HPC. And we have a lot of customers that have, that same, they realize they need to go from A to B, but they have that IT as a barrier. So, and so TotalCAE basically knocks out all of those IT barriers. And we deliver a turnkey HPC appliance and kind of give you a simulation as a service. So you can give us your workload, you push the button, you get the answers back. Everything that's in between that was TotalCAE's responsibility. We basically draw a circle around everything that's required to do HPC simulation. That includes the answer software, your license servers, the hardware of the cluster, the scheduling, the business logic of that, reporting tools, everything's included, and then we manage that for you. By offering simulation as a service, it makes it a lot easier for companies to quickly adopt best-of-class HPC ability cheaper and faster than doing it in-house. So it's very common that use case that BD had. We do that for many other customers. The next slide. So on our platform, there includes everything that you're going to need. It's to make sure everything runs. It has the software, like they mentioned, the portal that makes it very easy for users to submit HPC workloads without being experts in the scripts. You could also use ANSYS RSM, which we support. We have everything that you need to run the Viz server analytics. And if you have power users, like BD had a mix of users, there's always that users that say, you know what, the GUIs is great, but I really want to dig in and do some, very, scripted, complicated things. They can start with our scripts that are automatically generated for you and tweak them and do what you need. So the solution supports an entire range and class of engineers. Next slide. So one differentiation is that we, TotalCAE totally manages this cluster for you in your data center. We pick up your call in 4 rings or less for any issue. We have a lot of automated bots that are constantly looking for issues that could affect the cluster, like maybe a model ran a machine out of memory. Our system automatically will remove it from the pool so you don't end up having jobs die because of that. And then our team of HPC consultants logs in remotely and fixes everything for you, and so your jobs are not impacted by system issues. We take care of everything. The new version of ANSYS 19 comes out. We already had it upgraded for customers. And we take care of all your license upgrades, and you basically get a dedicated IT department just solely focused on engineering HPC included with this hardware appliance to help you keep your jobs running and make sure you can meet your deadlines. Next slide. One of the things that we included is the TotalCAE web portal, which, as Chris had mentioned, that makes it really easy to submit HPC workloads. So you actually, behind the scenes, this is a Linux cluster, but you never actually see Linux. You see this web interface, you just drag your models onto it, select the version of the application, push a button, and then you'll get an email when your job's done, and then you can log in and view or post-process the results. And also can do automated post-processing to make images like Chris would show where everything gets automated, beginning to end. Next slide. Often management is interested in getting analytics on, hey, we've made an investment in HPC. We'd like to make sure, that we're utilizing the resource. Often engineers are like, hey, I need more additional resources, or I need more ANSYS HPC packs. And with our analyzer, which comes included, we give you a full set of analytics so you can answer the questions for management, or be able to justify, hey, I need more resources, or you'll be able to say, hey, look how much workload is pending because I didn't have enough licenses. So you can justify getting additional HPC licensing. And you can kind of see who's using the cluster and various metrics to help make data-driven decisions on purchases of both hardware, software, licensing, and our services. All right, next slide. The Viz server was something that BD mentioned they recently added. And the Viz server, you can think of it like a mega workstation. It has high-end graphics. So you can go in, bring up the ANSYS applications, and you don't have to bring the data back to your workstation. So this is great if you have remote users, maybe your data center is a little bit far, or you can do things with this that you might not have been able to do before, like mesh very large jobs, because typically this workstation, super workstation, might have around 400 gigabytes of RAM. That's available to all users who log into it. And so you're able to solve big, large problems or mesh large problems, interactively that you might not be able to do on a laptop or a workstation, and really increases the velocity of which you can do your submit, pre-process, submit, run, post-process. And this all runs inside of a web browser. In terms of the appliance architecture, most of these clusters basically have a management server, a visualization server, and then a bunch of compute nodes which do all the calculation. And they're tied together with what's called a high-speed interconnect that is able to move parts of the problem between the nodes at a very low latency. So unlike your machines that you might have in your desktop where they're connected with what's called Ethernet, that's very slow in milliseconds range, and these special connections between these calculators are in the microsecond range, so it can move bits of data back and forth much faster. So it isn't just hooking up machines together. There is some special technology that goes into these systems. All of this is kind of handled by TotalCAE. You don't necessarily have to be an expert or even know any of this. It comes kind of pre-delivered in our appliance, and we completely manage it for you. Next slide. Next slide. So if you want to learn more, you can go to totalcae.com/ANSYS. We have a lot of information about the appliance, some videos on how it runs. If you'd like to, next is going to be Spencer, where he's going to talk about the HP hardware behind this, some benchmarks that you can see the kind of performance improvements you can get with ANSYS 19.
Thank you, Rod. Hello, this is Spencer Swift. I'm with Hewlett-Packard Enterprise, as mentioned earlier. My background is in computational fluid dynamics, and I'm going to be presenting some benchmarking we did with the ANSYS 19 suite on our benchmark systems. Next slide, please. And just to help frame our conversation and presentation here, we've had 3 versions of our large benchmark cluster that we maintain in-house. Each of these systems had 288 nodes. The first pair of systems, simply called Benchmark System 1 and 2 here, are detailed in the middle column. Those 2 systems were based around the Intel Xeon E5 2690 V4 processor, commonly known as Broadwell. It ran at 2.6 gigahertz, had 14 cores per socket, so each of our nodes had 28 cores available. We installed 128 gigabytes in each node, and that memory ran at 2400 megahertz. Now, the only difference between System 1 and System 2, System 1 had an interconnect based on Intel OmniPath architecture, and System 2 had an InfiniBand EDR interconnect. They both ran Red Hat 7.2, which was current at the time. Our third and still current benchmark system is the same infrastructure, but filled with Intel Xeon Gold 6154 processors, commonly known as Skylake. These run at 3 gigahertz. They now have 18 cores per socket for a total of 36 cores per node. Because of the additional nodes and additional DIMM capacity, we have now installed 192 gigabytes per node, and this memory runs at 2667 megahertz. This cluster is only based on the Intel OmniPath architecture for the interconnect, and it now runs Red Hat 7.3, which is now current. Next slide, please. So first, I will go into the benchmarks we have done using the ANSYS Mechanical 19 product. Next slide, please. So this first slide, we're presenting results for a single node going from 1 core up to all 36 cores. ANSYS provides a suite of 10 benchmarks for problems for ANSYS Mechanical 19, and we are presenting the geometric mean of all of them in this slide. So what we are presenting is elapsed wall time averaged over all 10 benchmarks. And if you look at the small icons at the bottom of the slide, which I realize are very small, they are actually representations of the geometries of each benchmark. And as you can see in the slide, where we're presenting wall time, so lower is better as we increase core count, we have good scaling from 1 core to 4 cores and again to 8 cores. We still have useful scaling to 16 cores, but the scaling flattens out once we hit 24 and 36. And remembering this is a geometric mean, and we will go into detail of each benchmark on the next slide, you'll see that some benchmarks continue scaling out to 36 cores, while a few do not, and those are the ones that cause the geometric mean to flatten out. Next slide, please. So here we represent the 10 separate benchmarks, each in a group of bars. And now we've increased the scaling a bit. We're now representing 1 node through 4 nodes, where 1 node is the lighter green on the left of each group, and the violet color is on the right, representing 4 nodes. Now we've broken out each problem, and you can see, looking at the very first model, which is a conjugate gradient number 1, we actually have pretty good scaling from 1 node to 2 to 3 to 4 nodes. Looking at the one next to it, the conjugate gradient number 2, that one only shows good scaling from 1 to 2 nodes and is effectively flat at 3 and 4 nodes. And you can look across the different models and see right in the middle, we have the V19 SP1, a sparse matrix number 1, and it shows basically flat scaling as well. But next to it, the sparse matrix number 2 shows good scaling. Again, we're showing wall time, so lower is better. Next slide, please. Now we are showing the ANSYS Mechanical speed up of the earlier benchmarks off of our system with the Intel Xeon E5 2690V4 processor versus the newer Intel Gold 6154 processor. Again, broken out across all 10 benchmarks. In this slide, we only have bars for 1, 2, and 4 nodes. We didn't have apples to apples data for 3 nodes. And you can see across all the benchmarks, there is a gain at all node counts between the previous generation processor and the current Gold 6154. There are stronger gains at 1 node where scalability and intercommunication are less of a factor than raw CPU power. Next slide, please. Now we'll move into showing results from benchmarking of the ANSYS Fluent 19. Next slide, please. And again, we start off with showing results on a single node going from 1 core up to all 36 cores. Again, ANSYS provides a suite of about 10 benchmarks for the Fluent product, but in this case, I've decided to break out a subset. So we're showing 1 model for this slide, which is their aircraft wing with 14 million cells. We would probably consider this a small to a medium-sized benchmark. And you can see very strong scaling all the way from 1 to 36 cores. On this slide and on the rest of the Fluent slides, we are presenting job throughput rating, which is jobs per day. So in this case, larger or higher is better. And that's why you see the graph growing from 1 to 36 cores. At 36 cores, you're getting more jobs done per day. And this is again on the Intel Gold 6154 processor. Next slide, please. And here we have 2 additional benchmarks, and we are now showing scalability from 1 node all the way up to 216 nodes of our system. Now, on the left, we have 2 new benchmarks. One is the F1 race car with 140 million cells. That would be a very large model with external flow. Next to it is the combustor problem with 71 million cells. That would be considered a medium grid mesh. However, this problem has a lot of physics, including chemistry going on, so it's a more complicated set of equations to solve. And then on the right-hand chart, we still have the same aircraft wing with 14 million cells as from the previous slide. And for all three models on the Gold 6154 processor, we see strong scaling all the way from 1 node up to 216 nodes. Next slide, please. And here we have a comparison based on just the F1 race car benchmark at 140 million cells between the Intel E5-2690V4 processor and the Gold 6154. And we go from 3 nodes up to 144 nodes. And the reason for starting at 3 was that in the benchmark system 2, the F1 problem was large enough it would not fit in the memory of less than 3 nodes. And you can see strong performance gain across the node count between the 2690V4 and the Gold 6154. Next slide, please. Now we're going to add benchmark results for the ANSYS CFX19 product. Next slide, please. And here again, we start with a single node going from 1 core to 36 cores of the Intel Gold 6154 processor. The model used from ANSYS is their Le Mans race car. And again, what we're representing is job throughput rating or jobs per day. So more jobs per day, higher is better. And we see strong scaling across the entire node. Next slide, please. Now we break out 2 models for increased scaling on the Intel Gold 6154 processor. The left-hand chart is still the Le Mans car model, now going from 1 node with 36 cores up to 16 nodes with a total of 512 cores. And we see strong scaling for job throughput again. The right-hand slide is an additional model. This is an internal flow model of an automotive power steering pump. This one scales from 1 to 32 nodes or 36 through 1,000 cores and strong scaling across that range. Next slide, please. And here is an additional model. This is an external flow over an aircraft wing. We have 2 charts for 2 different resolutions of the same airfoil. The left-hand chart is the airfoil represented with 10 million cells, and the right-hand chart is the airfoil represented with 50 million cells. Both show scaling from 1 node through 32 nodes, or 36 cores through 1,000 cores, and both show strong scaling again across the range. Next slide, please. And our final slide, based around the aircraft wing again, both at 10 million cells on the left and 50 million cells on the right, is comparing the Intel E5-2690V4 versus the Gold 6154. And the results are based on 1 node through 32 nodes, and we see strong scaling across the range for both models. If you look at the right-hand chart for the higher resolution mesh, you see greater gains between the 2 processors, and that's because with the higher resolution there's a lot more computation going on, and the intercommunication is still a smaller factor of the overall runtime as compared to the lower resolution model. Next slide, please. And now, in summary, we would like to represent or present to you a recommended starter cluster for any group or individual that might be moving from a desktop workstation or even a small group server for simulations going up to higher resolution or greater throughput. Next slide, please. And this would be based on our Apollo 2000 Gen 10 starter cluster. We recommend this as a beginning point because of its high density and small form factor. So in a traditional 2U unit, you have the choice of a separate head node based on our ProLiant DL360 Gen 10, or a single XL170R node that would fit into and be part of the Apollo 2000 chassis. Then for the actual compute power, you have a choice of between 2 or 4 ProLiant XL170 Gen 10 compute servers. And within the chassis, each of those XL170Rs could have up to 4 of the Intel Gold 6148 processors, which have 20 cores and run at 2.4 gigahertz. Now, in the benchmarking slides that I presented, we had been using the Intel Gold 6154 processor, which ran at a higher peak of 3 gigahertz. It also has a higher thermal envelope and is not available as an option in this small high density form factor. So for someone moving up to a starter cluster, we actually recommend the Intel Gold 6148 as a very strong and robust choice. If higher performance is a criteria, we can build other clusters still based on the Gold 6154 processor. So going with the Gold 6148 processor in an Apollo 2000 chassis with 4 nodes, you could have up to 160 cores available. For Fluent and CFX simulations, we recommend at least one SSD drive of about a ½ terabyte. We can have more, but we suggest at least one for scratch space. Total memory for the cluster, we recommend 4 to 8 gigabytes per core for this class of simulations, and your head node should probably have at least 96 gigabytes or more if you are also going to use the head node for anything like data visualization, data analytics, or even just data movement. The cluster interconnect could be based on Ethernet at 10 gigabits, gigabit, or we can also provide Intel OmniPath or InfiniBand EDR. For 2 or more nodes clustered together, we actually recommend the Intel OmniPath or InfiniBand interconnects. The operating environments could be Red Hat Enterprise at version 7, which is what we ran in our clusters, or we also support and have run SUSE Linux Enterprise at version 12 Service Pack 2. The workloads appropriate for a cluster like this would be Fluent up to about 260 million cells, and CFX simulations in the range of 74 to 260 million nodes. Next slide, please. Now, this is a recommended Apollo 2000 Gen 10 starter cluster for ANSYS mechanical problems, and if you look at the slide, it will look very similar to our recommendations for Fluent and CFX. Again, you can choose a head node that is either external to the 2000, and that could be a DL360, or internal using one of the XL170R blades as your head node. And then you can have 2 to 4 compute nodes of XL170R. Again, our recommended processor would be the Intel Gold 6148 with 20 cores at 2.4 gigahertz, and that would give you up to 160 cores in a 4-node chassis. Now, for the ANSYS mechanical products, we actually recommend starting with at least 3 SSD drives for scratch space configured with a RAID 0, and you can have more than 3. There's also options available for accelerators in this chassis. Now, for total memory, we actually recommend a bit more for mechanical problems. Here we suggest 8 to 16 gigabytes per core in the compute nodes, and the head node's still 96 gigabytes unless you're going to do other work on the head node, such as visualization or data analytics again. The interconnect options are the same. We can do gigabit or 10 gigabit Ethernet, and InfiniBand EDR or Intel OmniPath, with InfiniBand and Intel OmniPath being the recommendations for clustering 2 or more nodes. Operating environment is the same. We can do Red Hat Enterprise at version 7 or SUSE Linux at version 12 Service Pack 2. And the workloads appropriate for this would be mechanical in the range of 80 million degrees of freedom up to 550 million degrees of freedom. And if the problems are at the larger end, towards the 550 million, that's when we would recommend more memory per core. Next slide, please. And that is the end of my presentation of the ANSYS 19 benchmark results, and I will turn it back over to Wim Slutter.
Yeah, thank you. And let me quickly wrap up the presentation part of the webinar and end with a few final comments before going into the Q&A. First of all, I want to especially thank our guest speaker, Mr. Baziano, for his very interesting and informative talk, sharing his insights and experience from moving away from workstation and servers to clusters. And for many of you who are currently using Workstation, I trust that this can also be an eye-opener for you on the why and how to move to an HPC system. I also like to thank Rob Mack and Spencer Swift for their guidance on HPC for ANSYS. I think it's also quite noticeable that both TotalCAE and HPE have a very close technical collaboration with ANSYS. And Neil is mentioning that this is very important to ensure easing and accelerating HPC deployment and also for you. So let me go to the next slide. This is just also to point you to the partner pages from HPE and TotalCAE. You can best find them through ansys.com/HPC-partners, and then you can click on HPE, on TotalCAE, and find additional resources. As you can notice, there are quite some additional resources in the form of white papers, reference architectures, obviously also information about a starter kit that they were referring to in our today's